Ever get that feeling like when you're working on a project, and your code starts to get a little, well, a little bloated?
Yeah, I know exactly what you mean.
Like those pointers, especially when you're dealing with these massive arrays, it feels like they're just hogging all the memory.
It's a classic problem. All those log n bits for each pointer, it can really add up.
Right. And then you start thinking there have to be a better way, some way to slim them down.
Well, that's what's so fascinating about the research we're looking at today. It's all about these, well, they call them tiny pointers.
Tiny pointers. Okay, I'm intrigued. So are they like regular pointers, but, well, tinier?
In essence, yeah, they're all about challenging this assumption that pointers absolutely need, log in bits to reference an array of size n.
Which, when you think about it, that's pretty much how we've always approached pointers.
Right, but these researchers are showing that if you have just a little extra information, you can actually compress those pointers down to a fraction of their original size.
Okay, now you've got my attention. What kind of extra information are we talking about?
Well, the paper goes into detail about something called a deference table.
A deference table.
Yeah, basically you can't just shrink the pointers themselves without some way to translate them back to the actual memory locations.
Right, right. That makes sense.
So the deference table acts as a kind of lookup table,
Oh, I see.
It lets you decode these tiny pointers and get back the data you need.
Okay, that makes sense. But I imagine there's got to be a trade-off somewhere, right? Like nothing's free in computer science.
You're absolutely right. The trade-off is in the efficiency of this deference table, specifically what they call the load factor.
Load factor. Okay, can you unpack that a bit for me? I'm not sure I'm familiar with that term.
Sure. Think of the load factor as a measure of how full your deference table is.
Okay, so higher load factor means it's packed pretty tight.
Exactly, and that's good for memory efficiency, of course, but it might make those lookups a little slower. You might have to search through more entries to find the right one.
Ah, so it's that classic space versus efficiency dilemma.
Precisely. It's a balancing act that we see all the time in computer science.
So with these tiny pointers and this load factor thing, how much are we actually saving? Are we talking like a little bit, or is this really significant?
Oh, the results are pretty mind-blowing. Even when you aim for a load factor that's really close to 1, meaning you're using almost all the space in your deference table, you can still get these fixed-size tiny pointers down to brith log n bits.
Hold on. Log n? That seems unbelievably small.
It is.
Compared to the usual, log n bits, it's practically nothing. Almost feels like we're breaking the rules of information theory here.
You're hitting on a key point. It is far more efficient than what basic information theory would suggest. But by cleverly encoding those pointers and using that extra bit of information we talked about, you can achieve this remarkable compression. And it gets even more interesting when you start looking at what they call variable size tiny pointers.
Variable size, huh? Okay, I'm hooked. Tell me more.
So with these variable size tiny pointers, you can actually achieve an average size of just log bits
Okay.
for a load factor of 1/1K. And what's really amazing is that the chance of a pointer being, way larger than that average, it drops incredibly fast, like doubly exponentially fast.
Wow. So in a way, you could say these tiny pointers are almost always like perfectly behaved in terms of their size?
Yeah, that's a great way to put it. They've got this awesome combination of being super efficient and super reliable.
Okay, now I'm really starting to see the potential here. But this is all still kind of theoretical, right?
Well, that's where it gets even more exciting. The paper actually lays out 5 specific applications for these tiny pointers, and I think they're things that any computer science student would find pretty relevant.
Okay, let's hear it. What can we actually do with these tiny pointers?
All right, so let's jump into the first one. They call it relaxed retrieval. Imagine you've got this huge data set, like a massive library or something.
Okay, yeah, I can picture that.
And you need to store all this data efficiently, but you also need to be able to retrieve it quickly when you need it.
Yeah, that's key. Like if you had to search through that whole library every time, it'd be a nightmare.
Exactly. So with relaxed retrieval, you get to add a little hint, so to speak, when you store each piece of data. It's like leaving yourself a breadcrumb trail to help you find it later.
Oh, I like that analogy.
And here's the cool part. These hints can actually be encoded as those tiny pointers we were talking about.
Wait, really? So the pointers themselves can help us find the data?
Exactly. They kind of blur the line between, pointers and retrieval keys. It's a really clever way to use them.
That's awesome. So instead of having to build these big, complex indexing structures, you can just use these tiny pointers to guide you right to the data.
Yeah, exactly. It's a super efficient way to manage those massive data sets. Now, the next application is succinct binary search trees.
Binary search trees, oh man, those bring back memories from my algorithms class.
Aha, I bet. So, as you know, binary search trees are great for searching and sorting data quickly, right?
Yeah, they're super elegant.
But they can also take up a lot of space, especially when your data set starts to grow.
Oh, yeah. I remember spending hours trying to optimize those things for space. It was always a struggle.
Well, tiny pointers can help with that too. By using tiny pointers within the structure of the tree itself, you can make them much more space efficient. They call them succinct binary search trees.
So you're basically giving them a super compact makeover without sacrificing their performance.
That's the idea. You get the best of both worlds.
And if I had known about tiny pointers back then, my life would have been so much easier. Okay, what else have we got?
All right, the third application is all about stable dictionaries. Now, stability is super important in a lot of real-world systems.
Yeah, because you want things to stay in a predictable order, right? Even when you're adding and removing elements.
Exactly. But maintaining stability can be pretty costly in terms of overhead.
It's like trying to keep a stack of papers perfectly organized while someone's constantly shuffling them around.
Aha, yeah, that's a good way to put it. But what's cool is that these tiny pointers actually allow you to create dictionaries that are stable without adding much overhead at all.
Wait, seriously? So no more chaos, my data structures.
Less chaos, for sure. And it's especially helpful when you're working with lots of small values like control bits or flags in a system.
Okay, yeah, those could be a pain to keep track of.
Right, but tiny pointers help make sure they stay put and don't cause any unexpected surprises.
Okay, I'm sold on stability. What about the last two applications?
All right, so the fourth one is called variable size values. This is a problem that comes up all the time when you're dealing with real-world data.
Yeah, because not everything fits neatly into the same size box, right?
Exactly. A lot of traditional dictionaries assume that all your data elements are the same size, which is often not the case.
Right, like when you've got text strings or images or even complex objects.
Yeah, trying to force everything into a uniform size would be super inefficient.
Totally. So how do tiny pointers help with this?
They allow you to build dictionaries that can handle values of different sizes without having to waste tons of space on padding or complex allocation schemes.
So it's like having custom-fit storage containers for all your different data types?
Yep, it maximizes both your space efficiency and your flexibility.
That's awesome. So we can finally say goodbye to all that wasted space.
Well, a lot of it, at least. And finally, the fifth application is optimal internal memory stash. This one focuses on situations where your data is spread across external memory, like a hard drive.
Oh, okay, so when you can't fit everything into main memory.
Right, and as you know, accessing data on a hard drive is much slower than in RAM.
Yeah, it's like the difference between grabbing something from your desk drawer and having to go all the way to the library.
Exactly. So imagine you had a tiny, super efficient index that could tell you exactly where to find each piece of data on that hard drive in constant time.
So it's like having a GPS for your data.
Exactly. That's the idea behind optimal internal memory staff. Tiny pointers help you create this index so you don't have to waste time searching around on that slow external memory.
Okay, so they're like tiny but powerful signposts, pointing us right to the information we need.
That's a great way to put it. They really are quite versatile.
It's amazing how these tiny pointers can address such a wide range of problems. It's like they're a secret weapon for computer scientists.
I think so. And you know what's really interesting? All this stuff with tiny pointers, it actually ties back to a pretty classic problem in computer science: balls and bins.
Balls and bins. Oh, yeah, I vaguely remember that from my algorithms class. It was about distributing items into containers efficiently, right?
You got it.
Okay, I'm with you so far. But help me see the connection here. How do balls and bins relate to these tiny pointers we've been talking about?
So picture this. The keys you want to store in your deference table, think of those as the balls.
Okay, got it. Balls are keys.
And the available slots in that table, those are our bins.
Right, right. Bins are slots?
Now, the way we assign those keys to the slots, that's like deciding where to put the balls in the bins.
Ah, okay, yeah, I'm starting to see it.
It's all about how we distribute those keys, those balls, so that we don't end up with one bin overflowing while others are sitting empty.
Yeah, you want to spread them out as evenly as possible, right?
Exactly. That's the key to keeping your deference table nice and efficient. And the paper actually goes into this really cool strategy called iceberged.
Iceberg. That sounds kind of intense.
It is pretty clever. It's like a hybrid approach, combining the best of two classic balls and bins strategies.
Okay, break it down for me. How does this iceberg thing work?
So it starts off by randomly assigning the balls to bins, kind of like a simple hash function.
Okay, that makes sense.
But here's the twist. If a bin starts to get too full, like it exceeds a certain threshold they define, the strategy changes.
Oh, so it adapts.
Yeah. The next few balls that come along, they get multiple choices of bins, and they go into the least full one among those choices.
Ah, I see. So it's like a way to prevent any one bin from getting overloaded and keep things balanced.
Precisely, and that's the beauty of it. By applying this iceberg strategy to our dereference tables, we can make them even more efficient for those tiny pointers.
Wow, so we're talking about connecting these like theoretical balls and bins concepts to actual real-world performance improvements.
That's exactly right. It's a reminder that sometimes the most unexpected connections can lead to the biggest breakthroughs.
This has been an incredible deep dive. I have to admit, I was a little skeptical about these tiny pointers at first,
I get it. They do sound almost too good to be true.
but honestly, I'm blown away by the potential here. And the fact that it all ties back to these fundamental ideas like balls and bins, that's just, it's mind-blowing.
I agree. It just goes to show that there's always more to discover, even in those areas we think we understand really well.
And for our listeners out there, if this deep dive has sparked your curiosity, I definitely encourage you to check out the original paper.
Yes, absolutely. It's a fascinating read, and who knows, maybe you'll be the one to come up with the next big tiny pointers innovation.
Well, that's all the time we have for today's deep dive. Thanks for joining us, and keep exploring those amazing connections out there in the world of computer science.